Okay, so in Cengage, they take you through this trying to help you understand the Schrödinger wave equation. And basically what Schrödinger did was he was able to come up with a way of us trying to understand what the probability of an electron being in any particular location was. And they show these equations that are called wave functions. And I have to say, when I look at these, I think you've got to be really on the ball to get something out of it, because it's hard for me to understand what's going on in here. And frankly, I make it through lots of my daily life, even lots of my professional chemist life, without worrying about this too much. And so, but in trying to understand what the Schrödinger wave equation is telling us, like we approach every other graph in this course, let's look at the axes and try to understand what they have. So here is, it calls it a wave function, and it's got this across the bottom of these graphs, it's got distance from the nucleus. So right over here is not very far from the nucleus, frankly, is the nucleus. And over on the right-hand side is some distance away from it. And that's true for both of these two graphs. So here we have, as we move further away from the nucleus, this line, this probability function, this wave function gets smaller. And so that should tell us that the further we are away from the nucleus, there's less likelihood that we're going to find the electron. And so this wave function is a mathematical solving of Schrödinger's equation. But what's better, or what's even more useful to us, is this squared wave function. And to the untrained eye, these two graphs look exactly the same. But because these numbers are, this on the right-hand equation, this is a squared function, it really starts to give us some sort of it's this first step towards a three-dimensional understanding of where the electron would be. And so what I'm going to do is say down here is, imagine that you have this function and your distance from the nucleus is 0, i.e. the electron is right on the nucleus. If that were possible, then these two lines would have to somehow meet, right? And that doesn't show it very well in all of these graphs, but these lines, the vertical axis and the distance from the nucleus line never meet. So we never get down to the electron being present right at the nucleus. It's always some distance away. And if we square these numbers, because these numbers are getting smaller, the squaring them makes them even smaller, right? So these numbers are less than 1, right? And so any number that's less than 1 that's squared. So here's a number that's less than 1, it's a half. If I square a half, I get to a quarter. So a quarter is smaller than a half. So going from the wave function to the squared wave function means that these numbers over here on the right are even smaller. And so all of that is a way of saying that the wave function and the probability density of where we're going to find lowest energy electrons they are not at the nucleus. They're some distance away. And if we instead now say, okay, the electron is some distance away from the nucleus, where do we typically find it? Well, as we move further and further away, there's no probability at all. And so the probability density wave function squared graph says the chances of us finding the electron are not at the nucleus, because it never touches the nucleus. It's just some distance away. And the image that we're most familiar with is derived from that. So let's go look, if I go down a little bit further, okay, here is a smudge, a dot picture representation, otherwise known as a smudge, which doesn't tell you very much. But if we scroll down a little bit further, oh, hallelujah. here's something that looks a little more familiar to us. It's this sphere of the 1s orbital for the hydrogen atom. And what does that tell? Well, this tells us, hey, it looks like the electron in the hydrogen is in this spherical shape. But the thing that we may have just learned or just started to recognize, if I go back up, we know that at the nucleus, there is no probability. So that means that this is not a solid ball of probability. It's actually a hollow ball of probability, right? That the electron is very likely on the surface of this sphere, but very, very, very unlikely to be in the very center of the sphere. The probability of it being at the nucleus is very low, but just a little bit away from it, that's where we're going to find those electrons. And so the Schrödinger wave equation and the wave functions are mathematical ways of us understanding that, yes, the electron has various individual locations that we can predict where it's likely to be. And if we take all of those and add them up, or count them up, not add them up, count them up, then we would end up with this orbital for the hydrogen 1s electron. And we will find that electron most likely in this location, but not down in the center, not down in where the nucleus would be, but on this kind of hollow sphere. And so that's why sometimes we draw the 1s orbital as a dashed line circle around the nucleus rather than drawing it as a solid ball or solid stick or something like that. Does that help you at all, Kevin?
Yeah, I think that's really interesting when you explain it like that, how Schrödinger's equation helps us create like this area or volume of where we can predict they are. And I think those graphs were helpful. And I also think that if you're able to relate this to the idea of orbitals, because we just saw the 1s orbital, yeah, maybe this has probably helped a lot with the discovery of orbitals and their shapes, if you're at all interested in that.
Or discovery of our understanding of those orbital shapes, yeah. I mean, the solving the equations is a way of us being able to identify where we think those electrons are. And that works for us because it also, where we think those electrons are, helps us to explain a lot of the macroscopic reactivity of atoms and molecules. And so that's why it works for us. Only a very few people care what happens down on the atomic level. They care a lot about what happens on the macroscopic level, where we want things to react or to not react, right? And we want compounds that have particular properties. But Schrödinger's equation helps us understand where electrons are and why molecules and atoms react the way they do.
All right. Anything else to add, Dr. Hunter?
Oh, I'm full. Thanks.
Yeah, I think that was a lot of stuff to handle, and I don't think I want to try to understand the math, but I think you helpfully explained it very well to me. So
thank you. Thank you. All right. Awesome, Kevin. Thank you.
Yep. Thank you, Dr. Hunter. Have a good one.